In this segment, we'll derive the general straight line regression model. So the formulation of the problem is that given x1, y1, all the way up to xn, yn, so we're given n data points, what we want to be able to do is best fit y is equal to a naught plus a1x to the data. So that's what we're trying to do. So if we had, let's suppose, some points given to us as y as a function of x, what we want to be able to do is we want to be able to draw a straight line which will best fit all the data points which are given to us. So assuming, let's suppose this point is x of I comma y of I, then we know that this line we are writing as y is equal to a naught plus a1x. That means that if I choose this point right here, that coordinate will be x of I because it's the same x value, but the value of y, there will be a0 plus a1x of I. So this vertical distance which you are seeing here, what we are doing is, by using the least squares method, is to take all these vertical distances which we have, and we are trying to take the square of these vertical distances and trying to minimize them, the sum of them. So if you look at the residual which you will have here, which is e sub I, will be the observed value minus the predicted value. So that is this distance right here, and the observed value is y sub I, and the predicted value is a0 plus a1x of I. And what we're going to do is, when we say sum of the square of the residuals, so we are taking all these residuals, squaring them up, and then adding them up. What we are basically doing is that we want the sum of the square of the residuals, or the sum of the square of the residuals will turn out to be as follows. And we can expand this to write it in this particular form. So what do we want to do? We want to be able to minimize this value of SR in order to be able to find the best fit of the curve. If this is sum of the square of the residuals SR, how do we go about finding out the minimum of this quantity right here? That is the goal. So the sum of the square of the residuals is given by this expression now, right? And what we want to do is we want to make this sum of the square of the residuals, or SR, to be as small as possible. Make it as small as possible, which means that we're trying to minimize it, find the absolute minimum of that. And we can find with respect to a0 and a1, because y sub i's are fixed, x sub i's are fixed, so the only thing which is under control is a0 and a1. So how do we go about doing this? So let's do the first derivative part here. So the first derivative part of finding the absolute minimum of SR would be as follows, that hey, let's go and take the derivative of SR with respect to a0, and that'll be summation I is equal to 1 to n, and we can apply the chain rule here. We get 2 y sub I minus a0 minus a1xi multiplied by the derivative of minus a0, which is minus 1 with respect to a0. Same thing, we'll have del SR by del a1. Again, we apply the chain rule, we get 2 times y sub I minus a0 minus a1xi multiplied by, hey, what is the derivative of what's in the parenthesis here, which will be with respect to a1 would be just minus x sub I. And we want to put this equal to 0, and we want to put this equal to 0. And we want to be able to find out, hey, what would be those values of a0 and a1, so that the derivative with respect to a0 and derivative with respect to a1, the partial derivatives, will be equal to 0. Let's go and look at this equation. So what we're going to do is we're going to expand it. We're going to get as follows. So I'm basically taking the summation and breaking it up into 3 separate summations. I'm going to do the same thing here. I'm going to get So this one will be I is equal to 1 to n x of I, y of I there, because we have x of I minus x of I here. So don't forget about that. That's my plus 2 summation I is equal to 1 to n a naught x of I. And same thing, something similar here. So what you're basically seeing that here we're somehow ending up with two equations and two unknowns. And we're going to simplify it a little bit further to find out, hey, what do we get? So you can very well see that you have 2 here, 2 here, 2 here. So we can divide by 2. Same thing here, we have 2 here, 2 here, and 2 here. We can divide by 2. So let's go ahead and do that. So I'm going to divide both equations by 2. And if I do that, this is what I'm going to get. I'm going to get a summation of y terms here, summation of a naught here from 1 to n, and then a summation of a term which has a1 in it. Then the next equation, I'll get something like this. So basically what I have is two equations, two unknowns, and I want to be able to find out, hey, what are a0 and a1. So these are two known quantities, so I'm going to move them to the right hand side, because that's what we do when we set up simultaneous linear equations. We keep the unknowns on the left hand side and the knowns to the right hand side. But what is this? This is a0 being added to itself n times, so that will give me n times a0, right? And then I'm going to take a1 outside from here, and inside I'll get this, and summation y of I will go to the right hand side. So that's equation 1. Now let's look at second equation. I'm going to have this, so I'm going to take a naught outside, and x of I is getting summed here, and then a1 outside, and I'll have x of I squared being summed in the summation. But this quantity here will be moved to the right hand side because that's a known quantity. So now we can clearly see that I have two equations, two unknowns, and I should be able to solve them. So I'm not going to go through the algebra, but basically what I will do is I'll multiply equation 1 by summation of x of I, and equation 2 by n, and subtract. And why would I do that? Because that will allow me to get rid of a naught terms. So if I take this equation 1 multiplied by the summation of x of I take the second equation, and multiply it by n, what's going to happen is that the a naught terms will turn out to be the same. So I'm going to subtract the 2. So when I subtract the 2, this is what I'm going to get. I'm going to get a1 is equal to n times summation I is equal to 1 to n x of I, y of I, minus the summation of x values, summation of y values, that's in the numerator, and the denominator, what I will get is, I'll get something like this. So once I found a1, how do I find a naught? I can find a naught by going back to equation 1, because I found a1, which is right here, and I can plug it back into equation 1, and I can find out what a naught is. So let's go and do that. So if you look at equation 1, what did we have equation 1? We had n times a naught plus a1 summation of x of I equal to summation of y values. And so since I already know a1, I can find a naught. So this is what I get by simplifying, or by taking knowns to the right hand side. Keep in mind that this is a known quantity now, so that's why I was able to the right hand side. So I get something like this. And you can recognize that, hey, this is nothing but the average value of y, and this is nothing but the average value of x. So I get y bar minus a1x bar. So that'll be a naught. Okay, and just recall a1 will be this quantity right here. That is the numerator, and the denominator is this quantity right here. So we can find a1 and then we can find a0, and that's what gives us the best fit model. But that's not the end of it, because the only thing which we have done is the first derivative, taking the first derivative, partial derivatives with respect to a0 and a1 of SR, and put that equal to 0, and we got a single solution to the problem. But this, what does it mean? It means that the critical point is at a0 equal to this quantity and a1 equal to this quantity. It does not tell us that, hey, whether it's an absolute minimum. The only thing which it is telling us that, hey, this critical point can be a local minimum or a local maximum, a saddle point, or maybe even none of those. Let's go and see how do we convince ourselves that this also corresponds to an absolute minimum. The way it is the absolute minimum is because the second derivative test, when you conduct it, we're not showing it in here because that's a little bit beyond the scope of the course. The second derivative test tells us that a0 and a1 values found, they correspond to a local minimum. So we still don't know that, yeah, it's a local minimum, but is it an absolute minimum? How do we say that, hey, it's an absolute minimum? It's because of these. SR is a continuous function. Of a0 and a1. So that's one. And the second one is that del SR by del a0 equals 0. The first derivative part which we did only yields one solution. It did not give us multiple solutions. It gave us only one solution. So based on this, that the SR is continuous function of a0 and a1, that the first derivative being put equal to 0 only yielded one solution, that implies that a0 and a1 values found correspond to an absolute minimum. So the values of a0 and a1 which we found, they not only correspond to local minimum, but they also correspond to an absolute minimum, because SR is continuous function of a0 and a1, and that by putting the first derivative equal to 0, we got only one solution. And that's the end of the derivation of the linear regression model, and it is the end of the segment.